Okay. So, and then the next speaker should. Rachel, you're the next one?
Yeah, I'll stop.
Yeah, okay.
Don't worry.
Why don't you be by default the chairman of
I'd like to
until I'm finishing.
I'd like to advertise David will now speak on narrowscape.
Okay, so why don't we start? This is the first of 4 small lectures. I don't think, I mean, it's very hard, at least for me, to learn something in such concentrated a time period, because really the process of learning is about really repetition and coming back and showing things slowly on the board. I'll try to show some on the board, mostly on the slide, but I decided that for those of you who are going to stay here for the next couple of months, it's to do a class on the Friday from 2:30 to 5, where we can go slowly about all the different topics I would like to discuss. And basically, this is around the narrow escape. So the first name for narrow escape was the small hole theory. This was something like 2000. And then we move on to this name to calculate, to design the calculation, asymptotic calculation, for how long it takes for a stochastic process, or let's say a Brownian particle, to find a small hole. And then how do you calculate this time asymptotically? How it depends on the geometry? So we started this question because of the possibility to follow, it was 15 years ago, to follow single particle trajectory on the surface of a neuron, and the particle had to find a very specific location. And so we were interested in quantifying this. And so we developed some technique. There are other groups. I will mention other approaches, like what is called match asymptotics, to look at this question. And so this is really asymptotic on PDE, in partial differential equation, like elliptic PDEs. And then we moved on with this, because if we said that the time it takes to find a small target, this is also the time it takes for a chemical reaction to occur. And then we had this, we have seen this week these 2 other classes about non-spatial chemical reaction and how you go from spatial to non-spatial. I mean, what you have to change with some talk yesterday and this morning, we also use this to look at analytical calculation on Markov chains of some chemical reaction. And then how we analyze, and then we can use, we decided that maybe we could use all of this to analyze a large amount of data. And so let me show you what would be the 4 different topics of the 4 different lectures. The first one today is going to be about asymptotics and to obtain asymptotic expression for this narrow escape time. The second one is another type of passage time. This is the mean time to threshold. Suppose you have chemical reactions occurring in a domain and you have finite numbers. How long it takes, if you start, let's say, with 0 binding, you have A plus B that can bind together. How long it takes to get 10 AB molecules? Can you calculate this? What is the mean time to reach this? What is the distribution of those events? And you can formulate this as a Markov chain with specific absorbing conditions. Then the third talk would be about the analysis of empirical stochastic single particle trajectory acquired from super resolution microscopy, and how to do simulation in empirical domain. So what all of this means: suppose you are capable of getting tens of thousands of little trajectories recorded on the surface of a cell. What can you extract about the local diffusion tensor that can vary spatially, about the possible interactions. And those are short segments of trajectory. They do not cover the entire microdomains that you are interested in. So how, for example, can you get statistics about how you go from A to B if you can only have small pieces of trajectories? How you glue them together? And basically by the first part, which is the reconstruction, you can use this to do stochastic simulation of long trajectories that allows you to get the statistics you need about, let's say, going from A to B, which are far away, and they are not this is not covered by any statistic of the short ones. And finally, I would like to give 2 examples of applications of the narrow escape problem. One is in electrodiffusion, how you model electricity at the level of a microdomain, let's say 1 micron, which is the case at synapses of neurons. When 2 neurons connect, they're connecting by a synapse. And so PNP is a coarse-grained approximation of particles moving in a field that they are generating. So you have ended up having, you have a coupled system of partial differential equations. And you're interested, for example, how long it takes to find a small hole. And then a second aspect is about how you extend the narrow escape that is a theory for Brownian motion, to, let's say, a polymer model where you have correlated motion. And in particular, there are a fundamental question now that you know that in the last 10-15 years there's many experimental tools to visualize what happened inside the nucleus of a cell, how a particular spot on the DNA is moving, and there are more important or parallel data about what is the frequency at which 2 pieces of the DNA comes together. This is called the high-C data. And for example, an open question: if you break the DNA, if it's broken, and if some base pair are missing, then there is a template somewhere where this part here has to find by a random motion, by a stochastic path. It has to find a place somewhere. And it's not the motion of a single particle, it's the motion of entire polymer. So how long it takes for this to happen, and how this polymer model teaches about the real phenomena. All right, so so I'll try to now to move on to the first part, but before I wanted just to say things that are maybe we're going to be very quick on this. Okay, so before I have some materials in the website publications. I have also, in the last 5 years, because I was tired of repeating the same class over and over and over again, I decided to make a YouTube of the class so that it saves time both for me and the student. If the student doesn't want to come, they can stay at home. And so usually they are coming because it's important to see how things, you go on the board. So in this, I started to arrange all the recordings that are on YouTube. So if you go on YouTube, everything is disorganized. If you start with this link, I started to go slowly about, Ito calculus, how you go from Ito to Dynkin's equation and so on. And then I moved on to more research question. Okay, so just to motivate what we're interested in. So Sam showed you nice movie, and then I feel I had to intervene during his talk, because when you saw such a beautiful movie, you have the impression that we understand synaptic transmission, and it is clear what happens. So I want to go back and say, yes, those are great attempts, they are very important, those are our competitors. However, we have to go slowly about understanding the different processes that occur at the synapse. And for example, you know that if there is a mismatch of few nanometers between the presynaptic and the postsynaptic part, so basically a synapse is the connection between a neuron. This is one neuron coming. This is called the presynaptic terminal. This is called the postsynaptic terminal. Most of the time for excitatory cells, you could ask why this process doesn't touch directly the dendrite here. Why you need this particular protrusion with such a fancy shape? It's not understood. It's not clear why. So if you have a mismatch between the two, you know, this is, has been shown to be associated to a mental retardation type disorder. If, for example, in the case of autism has been just recently found in the last 10 years that it is due to some specific receptor. So we are talking here about 50 receptors, 50 channels that are playing a fundamental role between 0 and 50. So if some of the specific interacting protein are missing, this has been found to be associated to very complex spectral disorder autism. But nobody understands all of this. And yet, the number of molecules that we are interested in that are important here are not of the order of thousands. For the receptor, it's between 0 and 50. And for example, if you look at an important molecule, which has been discovered more than a few decades ago, that when calcium is going inside, whatever the mechanism by which calcium goes in, you have about hundreds to thousands of calcium going in. They have to bind calmodulin, another molecule. And then you have a holoenzyme here. And the number of these enzyme molecules turn out to be again of the order of 10, 20. And yet, those enzymes have been shown to be responsible for long-term memory. That is something that can last for months, years. So, and still we don't understand how they work. What's the mechanism? But clearly, what Dave Anderson showed, what Sam have shown, that with the possibility to make simulations in this microdomain, maybe the right tool to understand, for example, how many of these molecules can be activated. In particular here, what is very interesting is that this molecule has a geometry. It's like 6 binding sides, like you have a first ring and then you have a second ring. And there are some cooperativity. So the molecule by itself, even if you want to look at it in a coarse-grained manner, not to look at the details because it might be complicated for the simulations, but already with this statistical approach, you would like to understand how such a molecule can be activated and stay activated. Okay, so now I would like to go very quickly because most of what I wanted to say here has already been said during this week. So we're interested in modeling a microdomain where you can have, which is part of a cell. It is driven by molecular interaction. That's why it's so important to look at reaction diffusion or any kind of approach to model this, because they can underline a physiological function. That is, you expect that if you understand what happened with few molecules, this will tell us what the cell is doing, how the cell responds. For example, if you think about the presynaptic terminal here, an action potential, big depolarization is coming. Electricity, whatever that means here, so ions are flowing in, is responsible for the flows of calcium inside here. And the calcium, some of the calcium ion, have to find molecules just underneath the vesicles. And when there are sufficiently amount of calcium, the vesicle can release its constant neurotransmitters. So this is the cellular response triggered by molecular event. And so the idea is that with modeling, we can bridge this gap, how you go from molecules to the cellular event. So this is an example of the synapse. There's another example, so I will talk a bit tomorrow, but I think the second or the third workshop, Jürgen Reingruber, who developed many aspects of the phototransduction after we started all of this a couple of years ago, will discuss this question. And here's the problem. How a cell can detect a single photon. A rod, photoreceptors in the retina, they can detect the arrival of a single photon. Why? How? And so again, you go from a molecule that is activated. This is the schematic representation. You have a rod. You have about 1,000 layers of a membrane, and you have this molecule. So that I don't want to spend too much time here, but basically some aspect of the chemical reaction is on the surface of the cell, on the membrane. And the other second part is intracellular, until some channels here are closing. So if you can detect a single photon, it means that there should be a fantastic amplification mechanism, how you go from one to an entire cell response. Okay, and so I'll discuss a little bit this tomorrow. So this is just to motivate our ideas, how to go from molecule to a cell response. So we would like to understand, so why modeling this microstructure? Because we want to understand the function of the microdomain and analyze the behavior of the cell in normal and pathological conditions. So for example, we have been asked several years ago, what happens if you have a degenerated photoreceptor, which is what happened during some disease or during aging. If you change the shape of the cell, how this will affect the response of the photoreceptors, and how do you model this? So of course we have to account, and again all of this has already been said, but let me say it again. We have to account for the small structure, low numbers of low copy numbers of the molecules, the fact that sometimes you can have a dye that perturb the classical pathway. That's why you would like to do a simulation where you don't have all of this dye that were introduced to see the process. How to study a molecular cascade, so all the different steps after one molecule has been triggered. And of course, we'd like to predict the effect of drugs, molecules, when you remove a protein. So again, as we have seen this morning, the idea is we can use statistical physics to derive property to make coarse-grained model that will allow us to do simulations. And again, the gain of all of this is, maybe something that would be achieved in a couple of years from now, but to be able to reconstruct really the intact function, how the cell work. For example, in the case of photoreceptors, you can ask the question, what is the noise generated by such a cell, by the molecular event? Because of course, if you have a noise like this, and if you send a photon which is inside the noise, you will not see it. So what regulates the noise? So this is here, as we have seen in the previous talk, especially for the transcription and translation, you would like to calculate the variance of the noise, but also the power spectrum of the noise. What is the dynamics of this noise? When usually the noise is due to, you can simulate a noise with the power spectrum you want using a procedure that already exists. That if given a power spectrum, we know how to simulate this, but now you have a dynamical system, you have the noise at one point, you have an output somewhere, and you want to see what's the resulting noise, which ultimately, experimentally, in an empirical manner, is characterized by the power spectrum. Okay, so questions of interest: how cell maintain and regulate proteins number. So, for example, this is also a question that you can think about. If you have a protein that should maintain the memory, and its lifetime is, let's say, days, and the memory should be maintained for months. So the protein disappears, the cell somehow has to know, or I don't know how to say this, to express this, that it has, when this protein is dead, to replace it. So how the cell knows the number of protein that were there. It's not clear. Is it a question for us? I mean, for modelers, it's not clear either. This should not prevent us to think about it. So how structure define functions? Again, for example, how can we address the particular shape of a dendritic spine for calcium regulation, for diffusion? And of course, this is the need to, if we need to include geometry for partial differential equation and stochastic processes that can sample the geometry. And again, questions are how much molecules are involved, how long the process will take, and so on. Some biased references. For those of you, I mean, the Bible, the new Bible about molecular and cellular biology, this is a big book of Albert. It's bigger than, I think, any telephone book from any state. And you should not read it, you know, one page every day before falling asleep. You just use it when it's like a Wikipedia. But they did really a great job of for molecular and cellular biology. Now let me advertise for our own production. So there are 3 books by Schuss that about theory and application of stochastic processes. This is the old book. I think the prices on Amazon was $1,000. So this is, I'm sure we're not going to buy it with such a price. Though the price for the other one are more reasonable. And so recently we have this new book out, which is a summary. It will summarize and give more detail about the lectures that I will do here and the 4 mini classes of today. Further reading, like professional articles, I would say that for the narrow escape methodology, I would like to give credit to my friend and competitor from University of British Columbia, Michael Ward, who developed quite a lot of these asymptotics, this expression that I will show you, using match asymptotics, while we developed with Zev Schuss most of our analysis using Green's function. And so today I will show you the Green's function, but this approach gives also great results, and sometimes in the case, for example, of the ball, even more terms in the asymptotics. Okay, so we have seen already yesterday that the description of a molecule more than 100 years ago, Langevin proposed that we could use the Newton's equation for the acceleration. Then there was a friction force. Then you can add here the potential, and this will equal to the random noise. And then later on, fluctuation dissipation theorem came to explain why you need to have the friction here and the square root of the friction here, and epsilon is kT, k is Boltzmann constant, here the temperature. So basically, this type of equation has been used already for the last 20 years and more, for example, by people in channels to understand how, for example, ions not arrive to a channel, but suppose you have a bath here, how ions can go through a channel. And I have to say that I remember spending time in Chicago where they could not just do the simulations. They had one event every weeks or months having an ion going through. So it was really something very hard. At some point, they didn't continue, and then a few years later, Schuss proposed to use these equations because they were using before the Smoluchowski approximation to be able to calculate the fluxes, the fact that when ion goes through, it can go back before reaching, so looking at the probability to go through. And of course, this problem is still open, you know. We still do not understand much about how ions are going through a channel, why a channel can select a big ion can go through and a small one cannot. So This has to do with some packing ideas of how things happen inside, but this is still open. And there was the Nobel Prize, I think now it's a bit 10 years ago, by Roderick McKinnon, who crystallized the potassium channel. So we have a lot of information, but still how ions are going through, how they are selected, is still unclear. So this is the Langevin equation. So now it's the 100 years of the Smoluchowski paper. How you go from the Langevin equation to what is called the Smoluchowski limit of the Langevin equation, where this is the limit of large friction. It's where you have the system is overdamped, the particle after some time is going to be described by this. But if it is too short, I mean, if you have a particle somewhere, for this to be applied, you need to have sometimes the initial time here is disregarded. That's why, for example, when you do a simulation with this and you have an interaction with the particle, you have, as shown to you this morning, you have to place where the particle is going to be released somewhere else. However, if you have a velocity, then you don't have this problem, because the particle can be pushed according to the energy at which it started. But then the energy, the formalism becomes horrible, because then your phase space is not only x, but x and v. And this is extremely hard to work out something practical. Okay, so in general we have a stochastic equation where there is a drift term. This is a deterministic function. You can have a diffusion coefficient d of x that depend on the position. And this is going to be the model for what we are interested in. So let me remind you that the diffusion equation for the probability density function. So what is the probability to find a particle inside a volume dV around x, condition that it started at 0. So for a pure Brownian motion, this is, as we've seen this several times now, this is simply the diffusion equation. And what is important from this is we can calculate any quantity of interest. For example, what is the probability to find a particle in a subset A? You can use the information about the probability density function and integrate over A. So in general, if you have now a drift, the probability to find the particle at position x plus ds condition that it started at y. So the probability density function satisfies what is called the Fokker-Planck equation, dp dt equals d Laplacian p, plus the divergence of the force multiplied by p. So this is here the force for this stochastic process. And the initial condition, if you have the particle at position y, this is just the delta Dirac at y. Now I haven't specified in all of this the boundary conditions. And this is something not contained in the dynamics. This is something imposed by the physics, imposed by you when you do a simulation. For example, it can be purely absorbing. When the particle, when it reaches the boundary, is removed and permanently removed, then of course the probability to come back when you started at y to position x should be 0. Or you can impose a reflecting boundary condition. That is, if you have a particle hitting the wall, it is reflected, and this is expressed here by this condition. So now, if you are interested in average quantities such as mean first passage time for a stochastic process, or if you think about the stochastic equation where this is a diffusion coefficient, the Ito formula, the other way to show this, say that the mean first passage time to, let's say, the boundary, to obtain this quantity, you have to solve d Laplacian u equal -1 inside the domain, and u equals 0 on the boundary. So if you can solve this equation, this will tell us how long it takes. In general, nobody knows how to solve it. However, I'll show you that in the case of the narrow escape, this is where you can do asymptotics and you can calculate something. So maybe before this, let me give you another example. I'm not sure I will have the time to discuss much this, but suppose now you have a particle that can switch between two states. In one state, for example, it can diffuse with a diffusion coefficient d1, And in other state, it diffuses with coefficient d2. And for example, d1 can be very slow, very small. d2 can be very large. And still, the particle, suppose, can find a target only when it diffuses with a very small diffusion coefficient. And it switches at random time with a Poissonian rate between the two states. So how do you formulate the question of mean first passage time in that case? So I will just formulate here the question. So you can diffuse in a confined domain, you switch between the different states. The boundary, so you have here somewhere a boundary. Everything is reflecting here, except here where the particle can escape. For example, it can escape only in one state or in both states. And this will be reflected in the condition in the partial differential equation. And this is a problem coming from transcription factor that have to find the target inside the nucleus. So you can switch between state n and m with different rate, or you can diffuse. So if you look at the infinitesimal version of this, if you ask what happened between time t and t plus delta t. So either the particle switch between state m and state n according to this probability, kmn multiplied by delta t, or it can move according to the classical Brownian motion to a next position with such a rate 1 minus the sum of those rates. So why I'm presenting this right now is because the equations turn out to be surprising, because here you have to account, if you are interested in the mean first passage time, so the probability density function to start or to be at time t prime in state m at position y, this is where you started, and then you switch to position x, state n and time t. So you have to take care here of the initial position. And this is what is called the forward operator. For the mean first passage time, what you need to calculate is called the backward operator, which is the joint. And it turns out that you have to pay attention about the initial state where the particle started. And so the mean first passage time, this is, now you have to be more specific. What is the mean first passage time here? So we can say that what is the time spent by a particle in state n when it started initially in state m. So you have now a coupling between the time you spend in a given state and the initial state where you started. And so again, I don't want to spend too much time on this, but this leads to coupled systems of elliptic partial differential equation. For example, the time in state, when you started in state m, how long have you spent in state n? So this is solution of this equation. And for example, if you have 2, you ended up having 4 coupled elliptic partial differential equations. Okay. In general, we don't know how to solve this, so I'm going to focus on what we can solve. So the narrow escape problem. You start, actually it doesn't matter where you start. We will see why. How long it takes to reach here a small hole when the absorbing part of the boundary is divided by the total part is small. And let's assume B, there is no drift. If there is a drift, the situation is very complicated. If you don't have a drift that comes from a potential, the associated equation is not self-adjoint. It's non-self-adjoint equation. And then the mean first passage time doesn't necessarily mean anything, and you have to look at the different eigenvalues. And you can even have, for the probability density function, you can have oscillations, because you have complex, there is an imaginary part that can play a role. So I'm not going to discuss here. If you are interested, we did some work on this. So let me explain the ideas here. You start with the probability density function. which satisfies the Fokker-Planck equation, 0 at the absorbing part, reflecting everywhere else. So you can also look at the survival probability, the probability to find the particle still inside the domain at time t. And you can show that if you integrate the survival probability over x, and what you are left with is the initial condition, satisfy the backward equation with the absorbing boundary condition and reflecting boundary condition. There is no term here coming from the drift, because this is the adjoint of the Fokker-Planck equation. So there is no additional term. So then, in case where you have a self-adjoint operator, then you can expand in eigenvalues. They are all real. For long time asymptotics, you are sure that the particle will escape with probability 1. And so what you can remark is that the first eigenvalue is very close to 0 compared to the other one. So actually, you can neglect for a time sufficiently long enough the contribution of the other eigenvalues, and you are left with like a Poisson type process, the rate of which is exactly the 1 over the reciprocal of the mean first passage time. That's why the mean first passage time has some interest here. For time, again, if things happen too fast, and this can happen, suppose you start very close to the boundary, you can escape very quickly. So I'm not discussing here this case. I'm discussing where the particles start away from a boundary layer inside here this domain. Otherwise, you need a different type, which is called short time asymptotics, which I'm not going to discuss here. Okay, so let me skip this. Yes?
So just, you're making some comment about some operator needing to be self-adjoint. Which operator you're saying has to be self-adjoint?
Either the backward or the forward operator.
In what space?
So in the L2 space, you have to have...
Unweighted L2 space.
I'm sorry?
The unweighted L2 space?
You are here on the domain, you don't have to be any weight. You just, multiply by phi, you integrate, and you have this adjoint with respect, no weight. Well, I'm not in infinite space here. This is a finite domain, so I don't have to care about what happened at infinity. Okay, so I would like to go with you today, in the time that I have left, about how you calculate the mean first passage time in 2D and in 3D, and those are the results. In 2D, the mean first passage time equals the area divided by pi. D is the diffusion coefficient. Log is 1 over epsilon. Epsilon is the ratio of the absorbing to the total boundary. Note that at first order, this does not depend on the position where the particle starts. However, if you continue the asymptotics, the other one term does depend. It accounts for this. This is dimension 2. And this is dimension 2 for a regular boundary. We will see, I would like to spend some time on this. When you have a cusp, this asymptotic doesn't work. And cusps are important because sometimes if you imagine you have a protein, sometimes a site can be hidden inside the protein, and sometimes the site can show up. And this is due to a change of conformation. So this leads to different time scales. In dimension 3, if you have a circular patch, the mean first passage time is the volume divided by 4AD. A is the radius here. D is the diffusion coefficient. So this is a leading order term. And the second, there is a term, an unexpected term in the expansion, which is the mean curvature at the center here, multiplied by A log 1 over A, plus a term of order 1. So if you are a physicist, you would argue that why this is not correctly dimensional, because I put things in the order 1 term. That's the reason. This is unexpected. It comes from the singularity of the Green's function when you have boundaries. And this has been, this should have been discovered maybe 100 years ago. It was discovered by a Russian mathematician that there is a singularity term for the Green's function. Okay, there are more. I will skip this and let's go now, because this is supposed to be a class, to some how you calculate this, how you find this. You have the Dynkin equation, u equals 0, du dn equals 0 in the reflecting part, and you assume that the ratio of the lengths are small. So just one word about what are Green's functions. Green's functions have been used over the last, I would say, century, even more. This is very important, for example, in the theory of distribution. So you have a delta Dirac, and you are asking what is the solution of Laplacian. So this is the Green's function for the Laplacian. Laplacian J equals delta Dirac, and some boundary condition. So this is called, this one here, it's called the Neumann Green's function. And this term here has to be such that this is compatible. That is, if you integrate this, so if you integrate delta, what you get 1. And if you integrate Laplacian over the entire domain, you get only what remains on the boundary, and you get dj dn. And so if this is constant, the only possibility for this constant is equal to minus 1 over the surface. So what is the idea? The idea is that you have this Green's function, and you have this problem. So we are going to use Green's identity. Green's identity says that Laplacian u, so you multiply one equation by the other one, and you subtract. U Laplacian j, you do this, you integrate over omega, and this, by definition, is equal to d omega j du dn minus u dj dn. This is called Green's identity. So this is volume, this is surface. Now you just have to replace. Laplacian u equals minus 1, so this is minus 1, so this minus j. So this is the integral of j that you have here. Laplacian j is equal to delta Dirac, so you replace this by delta Dirac. So delta Dirac applied to u, it's u at the point. So this is u here at the point. And then you have this term on the boundary. So on the boundary, du dn by definition is 0, except on the small part. And then there is another term here, because the dj dn equals a constant, you have an integral of u, which we call a constant. And then the condition is that u has to be equal to 0 on this absorbing part. So this is an integral equation. What do we expect? What is the limit of u epsilon when epsilon goes to 0? U epsilon is the time it takes to escape. If epsilon goes to 0, the time should go to infinity, right? Because it gets harder and harder for the particle to escape. So this is actually a regular integral. Where is epsilon here? There is no epsilon. So when epsilon goes to 0, this is constant. U epsilon should go to infinity. So what we need is to balance something that goes to infinity. That can only be balanced using the c here, or using the this integral term. So now, if you write in the equation u equals 0, so this is 0, you have what is called an Helmholtz type equation. That is, you would like to find, so what are the unknown here? C is unknown, and the flux is unknown. The rest is known because it depends on the domain independent of epsilon, independent of the process. So this is where the geometry is hidden. Okay, so now what we need is to find what is the flux and what is this constant. So in principle, again, since the C here is an average of u, when you have to balance term even at a point which is on the boundary, when epsilon goes to 0, this is independent of epsilon. This C should depend on epsilon. The flux should depend on epsilon. And thus, this plus this have to be equal to 0. So let me skip the Green's function. Sorry. Okay. So now, let's suppose that the flux has a regular expansion. If you integrate d Laplacian u equal -1. You get integral of Laplacian u equals the integral on the boundary on the absorbing part, which is small. So if you have a regular expansion, you can just do a Taylor expansion, which is just du dn multiplied by the length of the interval. And this has to be equal to -1, and the integral of -1 is minus omega divided by d. So this tells us, for a regular flux, which is not the case in dimension 3, what is the flux at this particular point. And now if you use the second condition, which is u equals 0, in this equation, now what we need to look at is the constant c, because we have the flux. So now what we need for this is to calculate this integral. And so in dimension 2, it turned out that the Green's function can be written something that is singular plus a regular part. I'll finish in 2 seconds. So the singular part of the Green's function is log of 1 divided by the point minus, let's say, the center of this small hole. And this is, we know how to calculate, because this is really the log of the length of the boundary. J is a constant, so you can integrate this, and you get the constant c. And when you get the calculate the constant c, for a point which is far away from the boundary layer, you get this expression, omega divided by d, pi log of 1 over epsilon plus a term of order 1. Okay, I wanted to show you this because I think it's this contains all the ideas that we have developed for 10 years on this in dimension 3 and what happened when you have 2 holes. So I guess I have to stop. I didn't have I had I think 40 or 50 more slides. But I think Rachel is going to be upset if I do not stop here. So I'll stop here. Maybe tomorrow I'll continue a little bit on this, because I would like to discuss, and this will be for tomorrow, we'll resume at this position. I would like to start with a new type of problem that we started about narrow escape, which we call diastrait, the diastrait theory. This is how long it takes for a particle to find a target inside the cusp. And tomorrow I will tell you what are the asymptotics on this. All right. Thank you.
There's time for questions while I set up.